Um, so now we come up with this interesting question that if we simulate the chain long enough, then what happens? Intuitively, the uncertainty accumulates, and eventually we have no idea of what was the initial state. On the other hand, or equivalently, the information from the initial observation is washed out as we proceed throughout the time. For most chains, the distribution we end up in is independent of the initial distribution, but it's not always uniform as the last example we saw. This distribution is called the stationary distribution of the chain. Let's look at an interesting real-life example, which is web link analysis. You may know that every time you issue a query in a search engine like Google, an algorithm like PageRank is run over the web graph. The web graph is a graph in which every page is a state, and let's assume that the initial distribution is the uniform distribution over the pages or the nodes of this graph, and let's assume the following transitions. With probability C, we uniformly jump to a random page, which is shown by the dotted line in this graph. And with probability 1 minus C, we follow a random outlink from the current state, which is shown by the solid lines in this graph. And now the question is, given this initial distribution, which is the uniform distribution, and this transition probabilities, what if we run the chain long enough, what will be the stationary distribution of the pages or the nodes of the graph? The stationary distribution will spend more time on highly reachable pages, and it intuitively makes sense. For example, there are many ways to get to the Adobe Reader download page, and the stationary distribution captures this importance. In Google One, whenever you issued a query, it returned the set of pages containing all your keywords in decreasing rank. Now, all search engines use link analysis along with many other factors to specify which web pages are more important and are related to your specific query. Now let's look into hidden Markov models. Markov chains are not so useful for many agents. Eventually, you don't know anything anymore. As we saw, eventually you get to the stationary distribution of the chain, and the information you got from the initial state is washed out. So we need observations to update our beliefs about the world. Hidden Markov models are designed to exactly capture this. They have an underlying Markov chain over the states S, and furthermore, you observe outputs or effects at each time step, and that's crucial because it gives you more information about the state of the world or of the world that you can capture in your chain. As a Bayesian network, here is the structure of hidden Markov models. As mentioned above, there is a backbone Markov chain, and for each time step, we also have an observation from the underlying state of the chain. Now let's look at an example for the hidden Markov models. We use HMMs in this example to model the state of the day to be rainy or sunny as before, but in addition to what we've seen so far, we have another piece of information, whether we have seen an umbrella in a particular day or not, okay? And that is the emission or the observation, which is specific to HMMs, and we didn't have it for Markov chains before, okay? So an HMM is defined by three parameters. The first parameter is the initial distribution, or the probability of x1, the first day. The second set of parameters are the transition probabilities, which specify the dynamics of the underlying Markov chain, p of xt given xt minus 1. And the last set of parameters are emission probabilities. What is the probability of an observation in a particular state of the chain? Now let's look at the conditional independence assumptions encoded in a hidden Markov model. HMMs have two important independence assumptions. Firstly, the independence assumptions in the underlying um, Markov process, which is simply future depends on the past via the present, as we saw before. And secondly, current observation is independent of all the other variables in the model given the current state. Okay, so for example, E3 is independent of E1, E2, E4, X1, X2, X4, given that we have observed or fixed X3. And this is something specific to HMM, which we didn't have for Markov chains. And now let's look at a quick quiz. Does this mean that observations are independent given no evidence? And the answer is no. They are correlated by the hidden state, meaning that if we observe the hidden state, then the current observation is independent of the rest of the variables. But if we don't observe the current state, it correlates the current observation to the other variables in the model. That's the end of the mini lecture.